Welcome to Formal Methods, Lecture 11 Recap. Our topic today is implication. So what we have here in 3.57 is the definition of implication. A definition is the same as an axiom, so we will not prove it. The definition is P implies Q equivales P or Q equivales Q. And another definition or axiom is 3.58. This is called consequence. And we have the implication symbol reversed, pointing from right to left instead of from left to right. And the way we say this is P follows from Q equivales Q implies P. Again, this is an axiom, so we will not prove it. And now we have a couple of theorems. 3.59, implication. P implies Q equivales not P or Q. And 3.60, which has kind of the same shape as 3.57, P implies Q equivales P and Q equivales P. So 3.59, 3.60, and 3.61 are theorems that we can prove. The next theorem is 3.62. P implies parentheses Q equivales R close paren equivales P and Q equivales P and R. So 3.61 defines the contrapositive. P implies Q equivales not Q implies not P. Now there is some terminology that we should learn here that is not in the theorem sheet, the theorem document. This is the concept of the converse. So when we have an implication, P implies Q, the converse of P implies Q is Q implies P. So let's say for a moment that P is the proposition, it is raining, and Q is a proposition, the sidewalk is wet. Then the implication P implies Q is, if it is raining, then the sidewalk is wet. Now, on the other hand, the implication Q implies P is, if the sidewalk is wet, then it is raining. Now, the point here of this example is that an implication is not equivalent to its converse. For example, when you say, if it is raining, then the sidewalk is wet, well, that's obviously true, because if it's raining, the rain's going to fall on the sidewalk and the sidewalk's going to be wet. But the converse is, if the sidewalk is wet, then it is raining. And that doesn't have to be true, because maybe the sidewalk is wet because the sprinklers are on. You see? So the point is that an implication is not equivalent to its converse. On the other hand, when we are talking about the contrapositive of P implies Q, the contrapositive of P implies Q is not Q implies not P. And in this instance, an implication is equivalent to its contrapositive. In fact, that is precisely what 3.61 says. It says that P implies Q, this implication, is equivalent to its contrapositive, not Q implies not P. And so in this example, the contrapositive is, if the sidewalk is not wet, then it is not raining. And we see that that is equivalent to, if it is raining, then the sidewalk is wet. So that is an example of an illustration of how a scenario of how an implication is not equivalent to its converse, whereas an implication is equivalent to its contrapositive. Now let's prove 3.62. P implies, open paren, Q equivales R, close paren, equivales P and Q equivales P and R. So here we go. The proof. We are going to start with the left-hand side. P implies open paren Q equivals R close paren, and we are going to get it to the right hand side. So we have to end up with P and Q equivals P and R. So, first step, 3.60. With Q replaced by Q equivals R. Now, you should look up 3.60 now and write down what 3.60 is with Q replaced by open paren Q equivals R close paren. And if you do that, you should have gotten, boom, P implies open paren Q equivals R close paren equivals P and open paren Q equivals R close paren equivals P. And now what do we identify? We identify the fact that we have P implies Q equivals R on the first line, and this theorem says that P equivals Q equals R equivals P and Q equals R equals P. So what do we have on the next line? Boom. P and Q equals R equals P. Are you with me? Next step, 3.49, which we have reproduced here. P and open paren Q equals R close paren equivals P and Q equivals P and R equivals P. Now here is a situation that happens frequently when you have a string of equivals. And notice, what do we identify? We identify not only the P and Q equivals R, but we also identify the equivals P, like that. And so what do we have remaining? P and Q equivals P and R, which we simply bring down, and that was the right-hand side of what we were trying to get to. So the proof is complete. These theorems on implication, we just proved 3.62. 3.63 is the distributivity of implies over equivals. So we see that if you have P implies open paren Q equivals R, oh, that's just what we had on the left-hand side of 3.62. Another way to write it is P implies Q equivals P implies R, so it distributes. Now 3.63.1 and 0.2, 3.63.2 are not in our textbook, but it's quite interesting, and I have needed to use these theorems in another project before, so I included them here in our theorem reference document. So implication 3.63.1, the distributivity of implication over conjunction. P implies Q and R equals P implies Q and P implies R. And similarly with disjunction. So this is interesting because implication distributes over equivalence, conjunction, and disjunction. Interesting property of implies. And 3.64 is P implies open paren Q implies R, and it kind of looks like a distributivity, but we have an implication where we have an equivals. So it's P implies Q close paren implies open paren P implies R close paren. And then 3.65 is shunting, which is quite useful and well known in the propositional calculus. P and Q implies R equals P implies open paren Q implies R close paren. That we call that theorem shunting. Okay, so let's look at a few more. This is 3.66. P and P implies Q equals P and Q. 3.67. These are some other interesting theorems. I don't think I'm going to read them all for you. 3.71 shows that implication is reflexive. P implies P. And 3.72 is the right zero of implies. P implies true equals true. And then the left identity is true implies P equals P. So these will be important when they are the basis of a few meta-theorems that we are going to look at in the next chapter. 3.74, P implies false equals not P. And not P implies false equivals P, and P implies not P equivals not P. 3.74.1 and .2 are not in our textbook, but they are nice little theorems nonetheless. And 3.75 is false implies P equivals true. So false implies anything equivals true. Now the weakening strengthening theorems. 3.7, these are super important. 3.76a is called weakening the consequent. P implies P or Q. Now think about this. Do you see why this is logical? Well, I guess everything is logical in this system because after all it is logic. But look, if P is true, then for sure P or Q is true, right? Because in order for P or Q to be true, either one or the other has to be true. If either P or Q is true, then the whole thing is true. So P implies P or Q. So this terminology called weakening and strengthening, the left-hand side of an implication is called the stronger side, and the right-hand side of the implication is called the weaker side. And so the terminology for 3.76a is that P implies P or Q. That is called weakening the consequent because the consequent is weaker than the antecedent P. And then the other way around, 3.76b is P and Q implies P. So here again, P and Q is stronger than P. So we call that strengthening the antecedent. And we can combine these. P and Q implies P or Q in part C. Okay. I actually prefer 3.76.1 to the way our author has presented weakening strengthening. It's a little bit more general. So P and Q implies P and R. And then D and E, 3.76, D and E are variations on the theme of weakening and strengthening. 3.76.2 is interesting, which is not in our textbook. And now here's another interesting, a very well-known theorem. 3.77 is called modus ponens. This is used in philosophy a lot. This is the basis of deduction. If you know that P is true, and you also know that P implies Q is true, then therefore you can deduce, therefore Q is true. That's called modus ponens. But there's another one, there's another argumentation technique in English argumentation that is characterized by this well-known theorem in philosophy called modus tollens. And unfortunately, it's not in our textbook, but I think it should be. 3.77.1 modus tollens. P implies Q. If you know that P implies Q is true, and you know that Q is not true, then P cannot be true. That's called modus tollens. And then we have some more theorems here, 3.78, 3.78.1. I don't think I'll discuss them much. 3.80 is a really important one, mutual implication. P implies Q and Q implies P is the same thing as P equals Q. Mutual implication is used a lot in mathematical reasoning. Mathematics proofs frequently use mutual implication. And 3.81 is called anti-symmetry. P implies Q and Q implies P implies that that Q and P are equivalent. All right. And then transitivity. We have transitivity with implies. 3.82a has implies as the first conjunct of the antecedent, and then Q implies R as the second conjunct of the antecedent, and that implies that P implies R. And for parts B and C, it works the same way as part A does when you replace either one of those implications in the antecedent with an equivals. And also a characteristic of equivals that is not mentioned in the book, in our textbook, is that P equivals Q and Q equivals R implies that P equivals R. So equivals is transitive. And 3.82.2 is that if P equals Q, then P implies Q. So P equals Q is stronger than P implies Q. P implies Q is weaker than P equals Q. So that wraps it up. See you next time.